The F-14 Tomcat could transition from cruising speed to Mach 2.34 in mere minutes, while automatically adjusting its wing sweep to maintain optimal performance. This remarkable capability made it one of the most sophisticated fighter aircraft ever built. The Grumman F-14 Tomcat dominated naval aviation for over 3 decades, combining unprecedented engineering innovations with exceptional combat capabilities. Its variable sweep wings, advanced radar systems, and remarkable range of 1,840 nautical miles set new standards for carrier-based fighters. Despite its retirement from U.S. service in 2006, the F-14 Tomcat remains a testament to aviation engineering excellence, pushing the boundaries of what seemed possible in fighter aircraft design. This video examines the extraordinary engineering achievements that made the F-14 Tomcat a masterpiece of aviation technology, from its revolutionary wing design to its complex combat systems. Evolution of the F-14 design requirements. In the late 1950s, the U.S. Navy faced an escalating threat from Soviet long-range bombers capable of launching anti-ship missiles from beyond visual range. This challenge would shape the fundamental requirements for what would become the F-14 Tomcat. The Soviet Union's strategic bomber fleet posed a significant threat to U.S. carrier battle groups. Their primary aircraft included the Tu-95 Bear with a range of 9,300 miles and payload capacity of 33,000 pounds, and the Tu-16 Badger, capable of reaching speeds of 650 mph with a 4,500-mile range. These bombers could launch attacks from well beyond conventional fighter intercept ranges, necessitating a new approach to fleet defense. The F-14's design emerged from 2 critical requirements. First, it needed to serve as a fleet defense interceptor capable of engaging targets at extended ranges. Second, it had to function as an air superiority fighter. This dual-role capability was essential because carrier space limitations prevented the Navy from operating separate aircraft for each mission. To achieve this versatility, Grumman engineers developed an innovative solution: removable weapons pallets for the Phoenix missiles rather than permanent fixtures. This design choice allowed the F-14 to maintain an unrefueled combat radius of 500 miles, while retaining the flexibility to adapt its layout based on mission requirements. The demands of carrier operations significantly influenced the F-14's design evolution. After the F-111 Billion proved too heavy for carrier operations, the Navy initiated the VIX program in 1968. Grumman's response focused on creating a lighter, more agile aircraft capable of operating effectively within the confined space of aircraft carriers. The design incorporated specialized features for carrier operations, including robust landing gear for harsh takeoffs and landings. The engineering team also developed a variable sweep wing system that could adjust between 20 deg and 68 deg during flight, optimizing performance for both high-speed interception and low-speed carrier landings. The F-14's development marked a departure from the Department of Defense's initial push for commonality with Air Force aircraft. Instead, it represented a specialized solution to the unique challenges of naval aviation, combining the requirements for fleet defense, air superiority, and carrier operations into a single platform. Revolutionary variable sweep wing system. The variable sweep wing technology integrated into the F-14 Tomcat represents one of the most advanced feats of aeronautical engineering in its era. This innovative system grants the aircraft an exceptional level of adaptability by enabling the wings to shift between various configurations, each tailored to specific flight requirements. When positioned at a forward sweep of 20 degrees, the wings are optimized for takeoff and landing, providing enhanced lift and stability during these critical phases of flight. For cruising, the wings can be adjusted to mid-range angles, maximizing aerodynamic efficiency and fuel economy over long distances. At high speeds, the wings are swept back to a maximum angle of 68 degrees, minimizing drag and enabling the aircraft to achieve its remarkable top speeds. Additionally, the design includes an oversweep position of 75 degrees, specifically intended for compact storage on aircraft carrier decks, showcasing the Tomcat's operational versatility and its ability to meet the unique demands of naval aviation. This intricate system exemplifies the blend of precision and ingenuity that defined the F-14 as a groundbreaking fighter aircraft. The heart of the wing sweep system lies in its robust mechanical design. Grumman engineers developed hydromechanical screwjack actuators that work in perfect synchronization through mechanical interconnection. The system's cornerstone is a titanium box beam structure, created through Electron Beam Welding, a Grumman innovation that provided exceptional strength while reducing weight by 900 pounds compared to traditional bolted steel designs. The wing pivot points are positioned an impressive 8 feet, 11 inches from the fuselage centerline. This strategic placement allows for weapons mounting on the fixed wing glove, eliminating the need for complex swiveling pylons that had caused significant drag issues in previous designs. The central air data computer manages the wing sweep system through 2 independent electrical channels, ensuring redundancy. The system automatically adjusts wing position based on current Mach number and altitude, maintaining optimal lift to drag ratios throughout the flight envelope. For emergency scenarios, engineers incorporated a mechanical backup system. A dedicated emergency wing sweep handle connects directly to the hydraulic valves, providing manual control if the electronic system fails. The maximum wing sweep change rate reaches approximately 15 degrees per second under normal conditions. The variable geometry design delivers exceptional performance across diverse flight regimes. At high speeds, the swept-back configuration reduces the wing's thickness-to-chord ratio, enabling the aircraft to achieve its Mach 2.4 maximum speed requirement. During low-speed operations, the forward swept position increases lift and improves maneuverability. The system includes innovative features like inflatable canvas bags that seal the gap between the wing and fuselage during sweep transitions, ensuring smooth airflow. Additionally, retractable glove vanes on the fixed portion of the wing help manage the center of lift shift that occurs during the transition from subsonic to supersonic speeds. The engineering team's attention to detail extended to the hydraulic system design, where they implemented different pump configurations for forward and aft wing movement. Forward movement requires approximately 15 gallons per minute through a fixed displacement pump, while aft movement needs double that flow rate, managed by a variable displacement pump. Advanced materials and manufacturing. Advanced materials played a crucial role in achieving the F-14 Tomcat's exceptional performance capabilities. The aircraft's construction represented a significant leap forward in aviation manufacturing technology, combining lightweight materials with innovative fabrication techniques. The extensive use of titanium marked a revolutionary approach to fighter aircraft construction. Titanium components comprised approximately 25% of the F-14's structure, including the wing box and pivots, upper and lower wing skins, main structural longerons, and primary load-bearing elements. This strategic implementation of titanium allowed the F-14 to withstand maneuver loads of 7.5 G, though this was typically limited to 6.5 G in fleet operations to extend service life. The material's combination of lightweight, rigidity, and strength made it ideal for high-stress components, despite its higher cost and manufacturing complexity. The F-14's designers pioneered the use of advanced composites, particularly in the aircraft's control surfaces. The horizontal stabilizer showcased innovative material engineering through its boron fiber construction. This composite structure consisted of a main structural box with boron fiber, glass fiber front and rear beams, and aluminum honeycomb core sections. In regions requiring high shear strength, engineers developed a hybrid approach, using titanium overlays to distribute loads effectively across the composite structure. This early adoption of fiber composites positioned the F-14 at the forefront of aviation material technology. Grumman developed groundbreaking manufacturing processes to work with these advanced materials. The most significant innovation was the implementation of electron beam welding for titanium components. This technique proved particularly valuable in constructing the central box beam structure, which supported the variable sweep wings and absorbed flight loads. The electron beam welding process delivered exceptional strength while achieving a remarkable 900-pound weight reduction compared to traditional bolted steel designs. The manufacturing process required precise control of welding parameters and environmental conditions to ensure structural integrity. Engineers developed specialized fixtures and handling procedures to maintain material properties during fabrication. The success of these manufacturing techniques was dramatically demonstrated when a prototype F-14's box beam remained intact after a crash, validating the structural design and fabrication methods. Propulsion system development. Propulsion system development proved crucial in shaping the F-14 Tomcat's operational capabilities, with engine selection presenting significant engineering challenges throughout the aircraft's service life. The initial Pratt & Whitney TEF-30P412A engines, inherited from the F-111 billion program, delivered 20,900 pounds of static, uninstalled thrust each. However, these power plants became notorious for reliability issues. The engines were particularly susceptible to compressor stalls during high angle of attack maneuvers and rapid throttle adjustments, leading to the loss of approximately 40 F-14s throughout their service life. The wide engine spacing of 9 feet created additional complications. When one engine experienced a stall, the asymmetric thrust often resulted in unrecoverable flat spins. Navy Secretary John F. Lehman Jr. described the F-14-30 combination as probably the worst engine-airplane mismatch we have had in many years. In 1987, the United States Navy initiated a pivotal upgrade program for its fleet of F-14 Tomcats by equipping them with the directed F-110G400 engines. This enhancement brought about a substantial leap in both performance and reliability, addressing key limitations of the earlier power plant. The F-110 engines delivered a notable increase in the thrust-to-weight ratio, achieving an impressive 0.73 even at maximum aircraft weight. This advancement provided the F-14 with greater agility and speed, significantly improving its operational effectiveness in both air-to-air combat and strike missions. One of the most groundbreaking features of the F-110 engines was their ability to facilitate carrier launches without relying on afterburners, a capability that not only conserved fuel but also reduced stress on the aircraft. The engines also excelled at high altitudes, delivering enhanced performance above 30,000 feet, a critical attribute for intercept missions and engagements in the upper reaches of the atmosphere. The F-110G400 demonstrated remarkable reliability improvements over its predecessor. The engine featured a 3-stage fan driven by a 2-stage low-pressure turbine and a 9-stage compressor driven by a 1-stage high-pressure turbine, achieving an overall pressure ratio of 30.4 and a bypass ratio of 0.87. The F-110's sophisticated thrust management system incorporated an augmentor fan temperature controller, an early predecessor to modern FADIC systems. This digital control system managed both engine operation and variable exhaust nozzles, eliminating the need for mechanical controls. A notable innovation was the reduced arrestment thrust system, which automatically decreased engine thrust by approximately 10% during carrier landings to prevent overstress to shipboard arresting gear. The system activated when weight was detected on the main landing gear and the arresting hook was deployed. Despite these improvements, budget constraints slowed the transition from TEF-30 to F-110 engines. By 1996, 9 years after the F-110's introduction, only 126 Tomcats had received the new engines, while 212 aircraft continued operating with the original TEF-30 power plants. This gradual upgrade process meant that some F-14s continued flying with the problematic TEF-30 engines until as late as 2004. Combat Systems Integration. At the heart of the F-14 Tomcat's combat capabilities lay an integrated weapons system that set new standards in aerial warfare technology. The aircraft's combat systems represented a quantum leap in fighter capability, combining long-range detection with unprecedented multi-target engagement abilities. The AUG-9 radar system stood as a technological marvel in airborne intercept capabilities, maintaining its status as the most powerful radar of its kind until 2005. Equipped with a planar array antenna measuring 36 inches in diameter and delivering a peak output of 10.2 kilowatts, this advanced system was capable of detecting and tracking targets at extraordinary ranges and with unparalleled precision. One of the radar's standout features was its pulse Doppler search mode, which could identify bomber-sized targets at a staggering range of 277 kilometers. Equally impressive was its track-while scan mode, enabling the simultaneous tracking of up to 24 targets, an essential capability for managing multiple threats in complex air combat scenarios. The system's pulse Doppler single-target track mode further enhanced its effectiveness, providing long-range guidance for missiles in engagements requiring pinpoint accuracy. For wide-area surveillance, the range-while search mode allowed comprehensive detection over large operational zones. Additionally, the jam angle track mode played a critical role in counter-electronic countermeasure operations, enabling the radar to maintain performance even in heavily contested electromagnetic environments. The AWG-9's sophisticated signal processing capabilities allowed it to function effectively against aggressive ECM tactics, ensuring reliable targeting even under heavy jamming. Its emissions were designed to be exceptionally difficult for contemporary radar warning receivers to detect, providing a tactical edge by reducing the likelihood of adversaries identifying its presence. This combination of power, precision, and resilience solidified the AWG-9's reputation as a groundbreaking component of the F-14 Tomcat's arsenal. The AIM-54 Phoenix missile system represented the pinnacle of long-range air-to-air engagement capability. Operating at altitudes between 80,000 and 100,000 feet at speeds approaching Mach 5, the Phoenix could engage targets at ranges exceeding 100 nautical miles. The F-14's weapons control system enabled simultaneous engagement of multiple targets, with the ability to guide 6 Phoenix missiles against 6 different targets. This capability was demonstrated during the 6-on-6 missile shot test, where 6 missiles were launched over 38 seconds, resulting in 4 direct hits. The electronic warfare suite of the F-14 Tomcat represented a comprehensive and highly advanced defensive system designed to protect the aircraft against a wide range of threats in contested environments. Central to this suite was the AL-67 radar warning receiver, which utilized 4 strategically positioned antennae to provide the crew with full-spectrum coverage. This system was capable of detecting and analyzing radar signals from hostile platforms, giving pilots critical situational awareness and enabling timely evasive actions. To counter incoming threats, the AL-39 countermeasures dispensing set was incorporated into the aircraft. This system deployed chaff and flares as decoys to confuse radar-guided and heat-seeking missiles, effectively diverting them away from the F-14. By integrating this capability, the aircraft gained a robust layer of defense against both surface-to-air and air-to-air missile threats. Complementing these systems were the ALC-100 and an ALC-126 defensive electronic countermeasures. These components specialized in electronic warfare by jamming enemy radar and disrupting targeting systems. The system could analyze incoming radar signals and generate appropriate jamming responses, while the RWR provided precise threat direction and distance information. This integrated approach to electronic warfare gave the F-14 significant advantages in hostile environments, particularly when combined with its advanced radar and missile capabilities. The F-14's versatility extended to its weapons configuration, allowing it to adapt between air-to-air and air-to-ground roles. The aircraft could carry various combinations of AIM-54 Phoenix, AIM-7 Sparrow, and AIM-9 Sidewinder missiles, along with an internal M61, a 1 Vulcan cannon containing 676 rounds. Later variants incorporated the Lantern targeting system, enabling precision-guided bomb delivery and battle damage assessment capabilities. Carrier Operations Engineering. Engineering for carrier operations demanded exceptional innovation to enable the F-14 F-14 Tomcat's operation from the confined space of aircraft carriers. The aircraft's specialized systems represented a significant advancement in naval aviation technology. The F-14's catapult launch system incorporated sophisticated engineering solutions to handle the aircraft's substantial weight of 74,350 pounds. The steam-powered catapult system could accelerate the aircraft from 0 to 170 miles per hour in just 2 seconds. The launch system's effectiveness relied on several key components: computer-controlled pressure adjustment systems, reinforced nose gear for catapult attachment, variable wing sweep positioning for optimal takeoff configuration, and automated thrust management systems. The engineering team developed a unique feature, allowing the F-14 to perform virtually hands-off catapult launches, significantly reducing pilot workload during this critical phase. This automation represented a major advancement over previous fighters like the F-4, which required constant pilot attention to prevent either striking the water or over-rotating during launch. The recovery system incorporated robust engineering solutions to manage the extreme forces of carrier landings. The landing gear system featured a double nosewheel configuration and widely spaced single main wheels, specifically designed to withstand the intense stress of carrier operations. The aircraft's variable sweep wing system played a crucial role in recovery operations. During approach, the wings could extend to their maximum forward position of 20 degrees, providing optimal lift and control at lower speeds. In emergencies, the F-14 could even land with wings fully swept to 68 degrees, though this configuration significantly increased landing speeds and associated risks. Deck handling innovations focused on maximizing the efficient use of limited carrier space. The most notable feature was the wing's ability to oversweep to 75 degrees when parked, allowing the aircraft to overlap its horizontal stabilizers and minimize its deck footprint. This innovation proved crucial for carrier operations, where space management directly impacted operational efficiency. The twin-tail configuration served multiple purposes beyond aerodynamic performance. Its design helped maintain aircraft control at high angles of attack, while simultaneously reducing the overall height of the aircraft to fit within carrier hangar deck constraints. This engineering solution exemplified the careful balance between performance requirements and operational practicality. The F-14's deck handling systems included specialized features for rapid deployment and maintenance. The robust landing gear system, engineered specifically for carrier operations, ensured reliability and safety during both routine operations and emergencies. This system proved its worth during extensive combat deployments, with F-14s conducting 2,547 combat sorties during Operation Iraqi Freedom alone. The integration of these carrier operation systems demonstrated remarkable engineering foresight. During the Gulf War and subsequent operations, F-14s maintained high operational readiness while conducting combat air patrols, reconnaissance missions, and strike operations from carrier decks. The aircraft's ability to adapt to various mission profiles while operating from carriers validated its engineering design choices and confirmed its status as a cornerstone of naval aviation. Pilot interface and controls. The sophisticated interface between pilot and machine in the F-14 Tomcat exemplify the pinnacle of 1970s aviation technology, combining intuitive controls with advanced systems management capabilities. The F-14's cockpit featured a tandem seating arrangement that optimized crew coordination between the pilot and radar intercept officer. The cockpit's design prioritized visibility with a bubble canopy providing 360-degree views, enhanced by 4 strategically placed mirrors. Key features included a Kaiser-manufactured heads-up display projecting vital flight data, a vertical display indicator for navigation information, a horizontal situation display for tactical awareness, and advanced intercommunication systems for crew coordination. The VIDIG-R system significantly enhanced pilot situational awareness by displaying critical information including dive angle, angle of attack, airspeed, and altitude directly in the pilot's line of sight. This advanced display system reduced pilot fatigue and improved combat effectiveness across more than 10,000 flying hours. The introduction of the digital flight control system in 1995 represented a groundbreaking evolution in aircraft control for the F-14 Tomcat, enhancing both safety and performance. This advanced system replaced the older analog stability augmentation system while retaining the proven reliability of the aircraft's existing hydromechanical controls. By integrating digital technology, the digital flight control system significantly improved the Tomcat's handling characteristics and operational capabilities across various flight regimes. One of the key features of the digital flight control system was its anti-spin protection, designed to automatically provide corrective control inputs when the aircraft encountered high angles of attack. This feature greatly reduced the risk of spin events, particularly during aggressive maneuvers or adverse aerodynamic conditions. Additionally, the system incorporated logic to minimize Dutch roll, a lateral oscillatory motion, by implementing precise aileron to rudder interconnect functionality. This improvement enhanced the aircraft's stability and responsiveness, ensuring smoother flight dynamics in turbulent or high-speed conditions. The digital flight control system also played a vital role during carrier operations, offering enhanced controllability during challenging landing approaches. By refining control inputs and providing greater stability, the system facilitated safer and more precise touchdowns on carrier decks, a critical capability for naval aviation. The Central Air Data Computer managed critical flight parameters through its MEMP 944 chipset, operating at 375 kT and executing 9,375 instructions per second. This system controlled wing sweep positions and maneuver flaps while monitoring aircraft performance parameters. The F-14's emergency systems incorporated multiple redundant features to ensure crew safety. The fire detection system utilized dual sensing loops capable of detecting temperatures above 600 deg along their entire length, or 100 deg in localized sections. Emergency procedures included sophisticated engine restart capabilities with 3 distinct methods, including a spool-down air start for immediate recovery, a cross-bleed air start using a functioning engine, and a windmill air start requiring speeds above 450 knots. The emergency power system featured a dedicated generator driven by the combined hydraulic system, capable of maintaining critical systems within 1 second of main power loss. This system ensured the continuous operation of essential flight controls and avionics during emergencies. The fire suppression system employed a dual bottle design with low toxicity agents, strategically designed to minimize engine damage while effectively combating fires. The system's effectiveness increased at lower airspeeds, allowing the suppression agent to remain in the engine compartment longer. Maintenance and reliability. Maintaining the complex systems of the F-14 Tomcat required innovative engineering solutions that balanced accessibility with reliability. The aircraft's maintenance architecture represented a sophisticated approach to keeping these advanced fighters combat-ready. The F-14's fuselage incorporated strategically placed access panels that enabled rapid maintenance of critical systems. Engineers developed 2 primary types of access points: push-button activated doors for frequent inspection items and screw-secured panels for less commonly accessed components. This dual-access system proved essential for maintaining the aircraft's numerous internal systems while minimizing maintenance time. The design particularly focused on components requiring pre-flight inspection, incorporating quick-release mechanisms that reduced ground crew workload. The maintenance schedule for the F-14 Tomcat followed a meticulously structured 3-tiered approach, striking a balance between maximizing aircraft availability and ensuring comprehensive care for its complex systems. This system was essential to maintaining the Tomcat's readiness, especially during demanding combat operations. At the organizational O-level tier, maintenance occurred every 30 flight hours or monthly, focusing on quick component replacements and immediate repairs to keep the aircraft operational. This level of maintenance was designed for rapid execution, ensuring the Tomcat could return to service with minimal downtime. Intermediate I-level maintenance, conducted every 3 years, involved diagnostic testing and more detailed repairs, addressing issues that required specialized equipment and expertise. The most comprehensive level, depot D-level, maintenance was performed every 4 years or after 1,000 flight hours. This overhaul demanded intensive scrutiny and restoration of the aircraft, effectively resetting its service life. The modular design philosophy of the F-14 F-14 proved invaluable, particularly during O-level maintenance. Components were engineered for rapid swapping, enabling crews to perform essential tasks efficiently. This capability was critical during combat deployments, where minimizing turnaround time directly impacted mission success. Despite these efficiencies, the complexity of the F-14 became apparent in the sheer effort required for D-level maintenance. A single overhaul could demand up to 16,000 man-hours, involving specialized teams that included 6 avionics specialists, 3 armament technicians, 23 airframe and powerplant experts, and 6 quality control inspectors. These teams worked in coordination to ensure the aircraft met rigorous operational standards. The F-14's diagnostic systems also evolved significantly throughout its service life, incorporating advanced testing equipment to streamline fault identification and repair. Built-in test systems allowed maintenance crews to quickly detect and isolate issues in critical components, reducing downtime. The central diagnostic system further enhanced these capabilities by continuously monitoring key subsystems such as hydraulic pressure, electrical performance, engine parameters, and flight control responses. As the aircraft aged, maintenance requirements increased significantly. By the late 1990s, complete overhauls could take between 3 to 12 months. In extreme cases, restoration of stored aircraft required up to 42,000 man-hours of work, demonstrating the increasing complexity of maintaining aging airframes. The maintenance data recording system tracked component performance and failure rates, enabling predictive maintenance scheduling. This system proved particularly valuable for managing the aircraft's sophisticated electronics, including the ANOG-9 radar system, which required specialized attention due to its complexity. The engineering team's foresight in designing accessible maintenance points and modular systems helped extend the F-14 service life well beyond initial projections. Despite the increasing maintenance demands as the aircraft aged, the robust design of its maintenance systems allowed technical crews to keep these sophisticated fighters operational through multiple decades of service. The F-14 Tomcat stands as a testament to aviation ingenuity, combining groundbreaking technology with unmatched versatility. Its variable sweep wing system, advanced radar capabilities, and powerful F-110 engines redefined FIDEMs, while specialized features for carrier operations highlighted its adaptability to naval challenges. Despite its complexity and maintenance demands, the Tomcat's modular design and diagnostic systems ensured its readiness through decades of service. What aspect of the F-14 impresses you the most? Its engineering, combat capabilities, or role in naval aviation? Let us know in the comments and share your thoughts on what made this aircraft truly iconic. Thanks for watching.